Welcome again. Today we will discuss two more oxidizing agent. First one is manganese dioxide and second one silver carbonate on silicate. So, manganese dioxide is blackish or brown solid which occurs naturally, and if you see manganese oxide structure, it is 2 oxygen is there and its oxidation state is +4. It is mild oxidizing agent. It's oxidized primary alcohol to aldehyde and secondary alcohol to ketone. Also, it selectively oxidizes allylic alcohols and benzylic alcohols, that is its main application. Also, oxidation of saturated alcohol can be possible, but it need catalyst or high temperature. And the mechanism of this oxidation follows a free radical pathway. So, if you see the mechanism, first the oxygen of a manganese dioxide takes a proton from the OH and it becomes the oxonium ion, and then the O minus attacks to the manganese, activated manganese, and this species is formed. Now, there will be a, if you see the arrow, this is single electron arrow. So, now the single electron will circulate. If you see that the oxygen reacts with a H dot and OH is formed here, and one radical is formed here and another radical is formed on the manganese. So, this is a diradical. And this diradical then fragments, one electron comes from here and another electron goes to the manganese. So, manganese becomes manganese hydroxide. So, it becomes manganese hydroxide which is +2. So, manganese 4 becomes manganese 2. So, this is the reduction is happening, and here alcohol is becoming carbonyl compound. So, the oxidation is happening. Its application, it is mainly applied oxidation of allylic alcohols, conversion of allylic alcohols to alpha beta ethylenic esters and amides, which is called Corey-Gilman-Gonnem oxidation. This is also applied for oxidation of propargylic alcohols, oxidation of benzylic and heterocyclic alcohols, oxidation of saturated alcohols, and for that you need catalyst or high temperature. Cleavage of 1 to diols also is possible, hydration of nitriles to amides, dehydrogenation aromatization reaction which we have seen with DDQ, manganese dioxide also can perform these reactions, and oxidation of amines to imines, amides and diazo compounds. Also, oxidation of sulfur compounds to disulfide or sulfoxide, that we will see in details. So, first we will discuss oxidation of allylic alcohols. So, various kind of allylic alcohol can be oxidized with alpha beta unsaturated aldehyde. Here you can see this geranyl alcohol oxidized under manganese dioxide hexane 0 degree centigrade 30 minutes, it gives this aldehyde in 97% yield. Also, this jade allylic alcohol, where it oxidizes to this jade enone, and this is very selective, the jade it does not isomerize to the E enone. So, this is very mild condition. Also, this E allylic alcohol, this is a E allylic secondary alcohol which is also converting to the E enone selectively, and here the yield also 70%. Also, there is a dithiene motif is there and a secondary allylic alcohol. So, MNA to chloroform room temperature 96 hours, it gives selectively this product. Dithiene does not disturb under this condition. Here selective oxidation of also allylic alcohol in presence of other saturated alcohol is possible, like here a linear diol, where allylic alcohol is there, this is allylic alcohol and this is saturated alcohol. So, when MnA2 is treated with this alcohol in ether solvent and room temperature, only the allylic alcohol gets to aldehyde and the saturated alcohol remains unreacted. Also, steroid molecule where a secondary allylic alcohol and a saturated alcohol is present, under this condition only the secondary allylic alcohol gets oxidized to the alpha beta unsaturated enone and the saturated alcohol does not react. Also, a complex heterocyclic molecule, here you can see the 2 OH is there, both are allylic, but one is secondary, another is tertiary, and tertiary does not do any rearrangement like we have seen in PCC cases, but here selectively the secondary allylic alcohol getting converted to the enone with MnO2. Also, conversion of allylic alcohols to alpha beta ethylenic esters and amides is possible, which is called Corey-Gilman-Gonnem oxidation. So, here this geranyl alcohol first treated with MnO2 hexane 0 degree centigrade, it goes to the aldehyde, and that aldehyde can react with sodium cyanide, again oxidize to MnO2, and acetic acid in methanol condition, it gives the ester. So, it is a procedure to convert alpha beta unsaturated or allylic alcohol to the allylic ester. Also, this farnesyl aldehyde, when is treated with sodium cyanide and MnO2, acetic acid methanol, it going to the ester. So, this means that the aldehyde alcohol first goes to aldehyde, and aldehyde reacted with sodium cyanide to make a compound, and then it is going to oxidize again with MnO2, and then in methanol condition it gives the ester. The detailed mechanism we will see later. Here an alpha beta unsaturated aldehyde was treated with sodium cyanide, MnO2, isopropanol and ammonia. Under this condition the amide is formed from the aldehyde. So, here also the mechanism is same, but instead of methanol, ammonia is the nucleophile here, and that is why you get the primary amide. This is the mechanism. So, the OH aldehyde first reacts with cyanide to gives this compound, and then MnO2 oxidize this one. So, MnO2 oxidize this compound, which goes to the cyanoketone. And the cyanoketone then does a nucleophilic reaction. Nucleophilic substitution reaction, and here the methanol is the nucleophile here, and you get cyanide, ultimately HCN will be liberated and you get the alpha beta unsaturated ester. So, this is a 3-step process. For cyanide will react, then this is cyanohydrin. So, cyanide will react first aldehyde to make the cyanohydrin, and the cyanohydrin with MnO2 oxidize to the ketonitrile, and then a nucleophilic substitution reaction will happen to get the ester, and in presence of amide the ammonia acts as a nucleophile, and here methanol acting as a nucleophile. Also, oxidation of propargylic alcohol is possible, like this secondary propargylic alcohol under MnO2 chloroform room temperature condition, it gives the ketone in 74% yield. Also, dipropargylic secondary alcohol also with MnO2 gives the ketone in good yield. Here this alcohol, secondary alcohol, is both allylic as well as propargylic, and with MnO2 it gives the ketone in very high yield. Also, propargylic alcohol, here we have seen that here propargylic alcohol can oxidize first the propionaldehyde. So, first propionaldehyde is forming, and when piperidine is reacted with this one, then a conjugate addition is happening. So, you get a alpha beta unsaturated aldehyde with piperidine motif. So, this is a conjugate addition of the in situ generated propionaldehyde. Oxidation of benzylic and heterocyclic alcohols is possible, like here benzyl alcohol is converted to benzaldehyde with MnO2 chloroform room temperature condition. This is a very mild condition. Also, heterocyclic, so here secondary alcohol goes to the carbonyl in MnO2 condition is very good yield, 76%, and here you can see there is a benzylic alcohol, this is benzylic, and this is simple saturated alcohol, saturated primary alcohol. So, what is happening under this condition? Only this benzylic alcohol selectively oxidized to the benzaldehyde. So, this is also a selective oxidation of benzyl alcohol over saturated primary alcohol. Here you can see there is a acetal motif and allylic alcohol is there. So, acetal is not touched in this reaction condition, only the allylic alcohol is selectively oxidized. Here also propargylic alcohol is selectively as well as benzylic is oxidized to the ketone without disturbing the O-methoxy group. Here a ketyl group is present, and under this condition the ketyl group does not react, and only the secondary alcohol selectively oxidized to the carbonyl compound. And here furfural is used as the starting material, and under this Corey, Gelman, Gonem, reaction, the sodium cyanide MnO2 acetic acid methanol, it gives the furan ester in very high yield, 95% yield. So, oxidation of saturated alcohols with MnO2 also is possible, only we need some catalyst or high temperature. Suppose here these two catalysts are used for oxidizing the saturated alcohol to the carbonyl, 1.1 equivalent manganese dioxide and catalyst 2 as well as catalyst 3, which is a parabenzoquinone, and this is ruthenium complex. It gives in 28 hours reflux condition 66% yield of the product. Similarly, this normal chain secondary alcohol also under this condition 70 hours reflux, it gives 80% of this ketone. It has been found that cyclopropyl alcohol CH2OH also gives oxidation with MnO2 PET ether. This is a very mild condition, and under this condition this cyclopropyl CH2OH group oxidized to the aldehyde, and here a cyclohexanol 4-methyl cyclohexanol getting oxidized to the 4-methyl cyclohexanone under MnO2 mild condition 3 days, and it gives 71% yield. Also here it has been found the acetonitrile solvent is good when saturated alcohols are present, and here both saturated alcohol in the steroids getting oxidized to the carbonyl compound in very high yield. So, what has been found, the acetonitrile solvent is good when you want to oxidize saturated secondary alcohol. Oxidative cleavage of cis-1,2 diols, manganese dioxide can also perform cleavage like sodium periodate, and here it has been found that various cis diols can be cleaved to dialdehyde with MnO2, like MnO2 dichloromethane 4 hours room temperature condition, this diol gives the dialdehyde in 85% yield. Here also cis diol decalin system, it also oxidized to the dicarbonyl compound, because secondary alcohol it gives to the diketone and very high yield of the product is obtained. However, when the OH groups are trans to each other like this trans diol, here MnO2 does not work. So, this means that only cis diols can be oxidized with MnO2. Here we can see that the dialdehyde, here the cis diol, and this cis diol first goes to the dialdehyde, and then Huttig-Horner olefination reaction was carried out to get the product where the selectivity is 4.5:1. So, all EE versus EZ, that ratio is 4.5:1. So, this reaction is very good when the aldehydes are difficult to separate. So, under that condition you can treat the MnO2 product, that is the aldehyde product, directly with Horner-Huttig olefination condition, so that you can get the alpha beta unsaturated ester. Also, hydration of nitriles to amides is possible with MnO2. We know that potassium hydroxide or strong bases are good for cyanide hydrolysis, but here manganese dioxide can also do this reaction, and in hydrocarbon solvent active MnO2 gives only 30% yield of this benzamide. But when silica is present, then the yield got enhanced to 100%. So, that means under this condition the yield is very good for the benzamide product. Here an heterocyclic motif is present with the nitrile group, and with MnO2 condition these groups are undisturbed, but aromatization along with hydrolysis. So, aromatization plus cyanide hydrolysis is happening. So, this is dehydrogenation or aromatization, that we also will discuss later. So, manganese dioxide toluene 100 degree centigrade, it gives this product in very good yield, 82% yield we get this product. So, dehydrogenation and aromatization reaction, previously we have seen DDQ is mainly used for dehydrogenation and aromatization reaction, but manganese dioxide also can do this kind of reactions, like this compound diester, when treated with manganese dioxide in benzene reflux condition, it gives this benzene derivative in 92% yield. Similarly, when this unsaturated compound is treated with manganese dioxide benzene reflux condition, it gives anthracene in 89% yield. So, that means the aromatization is possible when manganese dioxide is used. Here a heterocycle saturated heterocycle motif is used for this reaction with manganese dioxide, benzene and pyridine was used, and as an added base in 55 degrees centigrade it gives this heterocycle in 69% yield. Also, when the cyclic hydrazone was treated with manganese dioxide, benzene, room temperature condition for 5 hours, it gives this pyrazole. Pyrazole product in 93% yield. So, different benzene and heterocycle motif can be obtained by aromatization with manganese dioxide. Oxidation of amines to imines, amides and diazo compounds is also possible, like here saturated tetrahydroisoquinoline was treated with manganese dioxide and dichloromethane, it gives the imine. So, here the aromatization does not happen when you treat manganese dioxide dichloromethane in room temperature, you get 89% yield of this imine selectively. And when an aromatic secondary amine was used like N-methyl aniline with manganese dioxide chloroform for 84 hours, you get N-methyl N-phenyl formamide. So, N-phenyl formamide is formed when N-methyl aniline is treated with manganese dioxide, and when a tertiary diamine is present with manganese dioxide, then the cleavage of this bond CC bond happens along with the oxidation to aldehyde. So, you get N-methyl N-phenyl formamide. So, this is N-methyl N-phenyl formamide. So, that means when an amine, secondary amine is used with MnO2, then the formamide motif is formed. On the other hand, when primary aromatic amine like 4-chloroaniline is used with manganese dioxide in PET ether solvent and 6 hours condition, it gives 87% yield of this diazo compound. So, primary amine gives diazo compound, secondary aromatic amine gives the formamide derivative, and this is secondary amine, this is primary aromatic amine. So, simple secondary amine can give imine, but when N-phenyl or secondary aromatic amine is there, then the formamide motif will form. Oxidation of sulfur compounds, here also when primary thiol or primary sulfide is present, then it gives the primary sulfides. So, primary sulfides give disulfide. So, this is very useful reaction. The manganese dioxide converts this thiophenol with molecular shift condition and reflux 100% yield, close to 100% yield of this disulfide is formed. Also, when an aliphatic thiol like butane thiol is treated with manganese dioxide, you get this disulfide in 92% yield. On the other hand, this is secondary sulfide. Secondary sulfide under this condition generates sulfoxide. So, this is very important. Primary sulfide will give the disulfide, whereas secondary sulfide with MnO2 aqueous HCl methanol. So, you need some acid also as well as MnO2, and then sulfoxide is formed in 98% yield. Also, this aliphatic secondary sulfide was converted to the sulfoxide with manganese dioxide, H2SO4 silica condition, 35 to 40 degree, you get 85% yield of this product. Here miscellaneous example. So, here this tetrahydrofuran alcohol, primary alcohol is oxidized to the manganese dioxide to the aldehyde by manganese dioxide, and then treated with Horner-Huttig ylide. This is stabilized ylide, and you get the alpha beta unsaturated ester in 6:1 yield. Also, when an N-Bock derivative is oxidized with MnO2, then the N-Bock group, this is not disturbed. So, N-Bock group is not cleaved under this condition manganese dioxide, and selectively the alcohol is getting to the aldehyde and then treated with this Horner-Huttig ylide to get the alpha beta unsaturated ester in 95%. So, this is very good method for converting alcohol to the alpha beta unsaturated ester, and particularly when the aldehydes are unstable, then you in situ you can oxidize with MnO2 and then treated with the Honor-Hutig ylide to get the alpha beta unsaturated ester. And this condition also very mild, like N-Bach group will not be disturbed. Here a bromo containing allylic alcohol was treated with this similar condition, manganese dioxide and Honor-Hutig ylide with a methyl group present here. You get this diene. So, first the alpha beta unsaturated aldehyde is formed and then the Hutig olefination is carried out, and here selectively you can see these two groups are trans to each other. So, the major product is the E isomer here. So, major product is E. So, because it stabilized ylide generally makes the E geometry. So, now we will discuss silver carbonate on silyte, which is called Fetijon's reagent, because the scientist Marcel Fetijon discovered this reagent in 1968. This is also mild oxidizing agent, generally suitable for both acid and base sensitive compounds. Reaction is carried out in nonpolar solvent like benzene or heptane. General reactivity, primary alcohol will gives aldehyde and secondary alcohol gives ketone. No over oxidation product obtained. Highly chemoselective, generally other functional group remain untouched. Selectivity, secondary alcohol oxidizes faster than primary alcohol. So, this is also special of Fetijon reagent. And the reactivity order is benzylic or allylic alcohol reacts much faster than secondary alcohol, and secondary alcohol reacts faster than primary alcohol. Also, the reaction is inhibited significantly by polar groups within the reaction system as well as steric hindrance of the alpha hydrogen of the alcohol. So, what is the mechanism of this reaction? The mechanism is that the chemizoption of the alcohol over the surface of silver happened, and then the alcohol, oxygen as well as the alpha hydrogen binds with silver, and ultimately the silver 1 goes to silver 0, and here H plus is formed as well as oxonium ion, and this oxonium ion finally gives the carbonyl compound. So, what is the overall reaction? The overall reaction is the alcohol plus Ag2CO3, you get carbonyl compound 2Ag, water and 1 molecule of carbon dioxide. So, Ag plus 1 to it is going to a silver, Ag 0. That is why it is getting reduced and the alcohol is getting oxidized. It is useful for the oxidation of allylic alcohol like MnO2. Here a TBS group is there and a ester group is present, and selectively with silver carbonate or silyte in benzene reflux conditions, allylic alcohol is getting oxidized and this group are untouched, a TBS group as well as ester group. Also, selective oxidation of a primary or secondary allylic alcohol is possible over other alcohols, like in this triol here this is the allylic alcohol and this is a secondary saturated alcohol, this is primary saturated alcohol, and when you treat this compound with silver carbonate on silyte in benzene reflux condition, you get only selective, this allylic alcohol is getting oxidized to the carbonyl compound and you get 70% yield of this product. 1,4-diol and 1,5-diol gives lactone. Like this diol, when was treated with silver carbonate, it gives first the aldehyde, one alcohol oxidized to the aldehyde and then it gives the lactol. So, lactol is formed and this lactol then oxidation gives the lactone. Also, when a pentane diol is used with silver carbonate and silyte benzene reflux condition, you get this lactone is good yield. Selectivity, secondary alcohol oxidizes faster than primary alcohol, like this diol is there, this is primary alcohol and this is secondary alcohol. So, with silver carbonate or silyte benzene reflux condition, only the secondary alcohol getting oxidized and primary alcohol untouched, does not react in this condition. Also, when a symmetric diol is used, like both are secondary, here one alcohol can be oxidized and you can get the beta hydroxycarbonyl compound in good yield. Here silver carbonate benzene reflux condition is used. Also, silver carbonate is used for rearrangement reaction, like this trans bromo compound, trans bromo alcohol, when treated with silver carbonate silyte, you get almost 1:1 mixture of cyclopentane carbaldehyde plus epoxide. On the other hand, when cis compound was treated with silver carbonate silite condition, you get cyclohexanone as the major product and this product is minor. So, this is typical Fedizon oxidation product. So, what will be the mechanism? So, generally bromo compound is bind to the silver, and what happens, this bromo compound is getting activated and then a rearrangement will happen and you get this compound cyclopentane carbaldehyde, and also there is a possibility of the epoxide because they are trans. So, you can get also epoxide. On the other hand, when cis is used, that time because they are cis to each other, so they cannot rearrange and form the epoxide. So, that is why rearrangement product is very less, only the cyclohexanone is formed. So, most likely first it getting oxidized to the 2-bromo cyclohexanone and then silver carbonate converts to this to cyclohexanone. Fragmentation reaction of the alcohol with the alkyne as a leaving group is possible with this reagent, and generally this propargylic secondary alcohol with silver carbonate on silite in benzene reflux condition, it gives the ketone, and alkyne as a leaving group. So, this alkyne is getting eliminated or fragmented under this condition. Also, fragmentation as well as selectivity is possible. Like this steroid molecule, here you can see there is a propargylic alcohol as well as another secondary alcohol which is homoallylic, and when silver carbonate on silite in benzene reflux used, only this propargylic alcohol is getting fragmented and converting to the ketone, and this homoallylic alcohol not oxidized under this condition. On the other hand, this substrate where is a both allylic alcohol as well as propargylic alcohol is present, and with silver carbonate on silite benzene reflux condition, it cannot distinguish between these two groups and both gets oxidized. So, here a saturated ketone is formed and here an unsaturated ketone is formed, generally in good yield. Also, Fedizon reagent has been used for dimerization reaction of phenol derivatives. Here 2,6 disubstituted phenol, and when R is equal to CH3, R is equal to CH3 which is isopropyl and tertiary butyl. So, when 2,6 disubstituted phenol is treated with silver carbonate, then this quinone compound is formed, and quinone compound is formed generally first this quinol will form and which also oxidize with silver carbonate to get this quinone. Here the redox potential of the reagent silver plus electron to silver is 0.80 volt, is high enough to oxidize the dimer to extended quinones, and these diphennoquinones are reduced by sodium hydrosulfide in weakly alkaline solution. So, sodium hydrosulfide converts this quinone diquinone to the quinol, and then these diphenols could be readily oxidized to the parent quinones by silver carbonate. So, this means that this first getting to the dimer product, dimer diphenol product, and then it is going oxidized with silver carbonate to the diphennoquinone. Also, if you want to get back this, then we can treat with sodium hydrosulfide to get this phenol, diphenol compound. And it has been found that when a methyl group is present para to the OH group, then this conjugated dione system is formed. Here also we can use different substitution like both methyl and both tertiary butyl and one methyl and another tertiary butyl, but para position will be CH3 group. Then you get this quinone system, and then with treatment with zinc acetic acid you can get this bisphenol system, conjugated bisphenol system, which on oxidation with silver carbonate gives this quinone, conjugated quinone motif. So, on reduction with zinc acetic acid, these quinones give the 4,4-dihydroxy stilbenes, which are reconverted to the stilbene quinones by oxidation with silver carbonate. And the dimerization probably occurs via intermediate benzylic radical. So, most likely when CH3 group present to the para to the OH group, and if there is substitution is there like methyl, then this benzylic radical is formed, and this benzylic radical first goes to stilbene phenol. First may be the saturated compound, first may be saturated and then the unsaturation. So, when a methyl group is present, then this conjugated enone system will form. And now, when this para position instead of methyl group, if tertiary butyl group is there, suppose R dash here tertiary butyl group, then it has been found that this peroxide is formed. Because now there is no possibility of the benzylic radical, so only now phenoxy radical will form. Phenoxy radical is formed, which dimerize under this condition, oxidative dimerization, and it gives this peroxide compound. Oxidation of 2,4,6 tri-tert-butyl phenol in benzene solution under atmosphere gives the free radicals. In the presence of air, it gives the peroxide. So, when there is a methyl group, then the benzylic radical is possible, and that case you can get this kind of system and dienone with the quinone motif, and when there is a tertiary butyl group, then the phenoxy radical will form and then the peroxide will form. Now, relative rate also has been found with silver carbonate reaction. So, when there is a group which can bind to silver, then the rate of the oxidation will get reduced. So, like this bridge system, here no olefin is present, but here there is olefin, and if these two alcohols, both are secondary alcohols, are treated with MnO2, then the relative rates has been found 50:1. So, without double bond, that substrate reacts 50 times faster than this compound. The rate limiting step of this reaction is proposed to be the initial association of the alcohol to the silver ions. We have seen that alcohol binds to the silver as well as the alpha hydrogen. So, this binding is very important. As a result, the presence of even weakly associated ligands to the silver can inhibit the reaction greatly. So, if there are ligands on silver, then the reaction can decrease. The rate of the reaction can decrease significantly. Additional polar functionalities of the reactant should also be avoided whenever possible, as even in the presence of an alkene can sometimes reduce the reactivity of a substrate 50-fold. So, that is what we have seen here. So, that means the double bond is binding with silver here. So, there is a competing reaction is happening with the silver double bond as well as the OH and alpha hydrogen. Even slightly polar solvents of any variety such as ethyl acetate or methyl ethyl ketone are avoided when using this reagent, as they competitively associate with the reagent. So, ethyl acetate polar solvents should be avoided. Commonly employed solvents such as benzene and xylene are extremely nonpolar, and further acceleration of the reaction can be achieved through the use of more nonpolar heptane. So, choice of solvent is very important in silver carbonate or fatty zone reagent oxidation. We have to use very nonpolar solvent like benzene, xylene, and sometimes you can add also nonpolar heptane. So, in today's class we have seen manganese dioxide oxidation and silver carbonate, which is Fettigen reagent. So, manganese dioxide does many reactions, like it is major application is oxidation of allylic as well as benzylic alcohol. It can selectively oxidize benzylic alcohol or allylic alcohol in presence of other saturated alcohols, and oxidation of saturated alcohols is also possible, but you have to use high temperature or other catalyst. Also, cleavage of diols, cis-1 to diols, we have seen this is also a reaction which is generally carried out sodium periodate, but here manganese dioxide under very mild condition can cleave cis-1 to diols. Also, if these dialdehydes can be treated with in situ with Horner-Huttig reagent to get the alpha beta unsaturated esters in good stereoselectivities. Also, Corey, Ganem, they have reported in situ reaction with sodium cyanide, the aldehyde with sodium cyanide, MnO2 and acetic acid condition to give the alpha beta unsaturated ester when methanol is used, also alpha beta unsaturated amide CONH2 when ammonia gas is used. Also, MnO2 has been found for different dehydrogenation and aromatization reaction, which we have seen with DDQ. So, manganese dioxide also can perform different aromatization as well as dehydrogenation reaction. So, different saturated heterocycles as well as benzene derivatives can be converted to unsaturated heterocycles. So, heterocycles or aromatic heterocycles and aromatic benzene compounds in very good yield. Also, sulphide compounds, if we have primary sulphide, then we get disulphide, and if there is a secondary sulphide, then we get sulfoxide. Also, amine compounds can also be converted to imines when there is a secondary amine, saturated secondary amine, that can be converted to the imine, and when there is an N-phenyl or aromatic amine is present, then we get the formamide derivative. Also, if the aromatic amine is present, then we get the diazo compound. Now, with silver carbonate or Fettigen reagent, we have seen that this is very useful for oxidizing benzylic allylic alcohols. Also, its reactivity is more than primary alcohol. So, secondary alcohol much more reactive than primary alcohol, and also it has been found that in the diol where primary and secondary alcohol is present, secondary alcohol is getting selectively oxidized to the ketone and the primary alcohol is getting untouched. Also, different fragmentation reaction like Fuparzylic alcohol can be fragmented with silver carbonate with liberal of acetylene, you can get the carbonyl compound, and this reaction also is much faster compared to other saturated secondary alcohol. Also, we have seen that rearrangement reaction, like when trans-bromo derivatives are there, trans-bromo cyclohexanol is used, then cyclopentane carbaldehyde is formed, whereas the cis compound there is no such rearrangement and simple cyclohexanone is formed. And lastly, we have seen the substrate when there is an internal double bond is present. So, that substrate is much less reactive compared to the substrate where no double bond is there. That means, there is a competition for the binding to the silver. The double bond can also bind, and that is why the reactivity or the rate of this reaction is significantly decreased. And also, in this silver carbonate reaction, you have to use non-polar solvent like benzene, toluene, also you can use heptane, but polar solvent like ethyl acetate or ketone compounds should not be used. I hope you have enjoyed. Thank you.